Hi, this is Ms. Schultz. So I'm giving notes on identities derived from the sum and difference formulas. And let's get started. So an overview of the problems we're going to do is we're going to prove sum and difference identity for tangent, given one for sine and cosine. Then we're going to do sine of a double angle. And then we will do sine squared, which is power reducing identity. Then we're going to prove the sine of a half angle formula. And we're going to do this one, and then this, and that's it. All right, so let's get started. So it gives us a hint right here that says, oh, does it not? No, it doesn't give us a hint. All right, so when we see tangent, a good thing to do is to rewrite it in terms of sine and cosine. So let's do that. So tangent of alpha plus or minus beta would be sine of alpha plus or minus beta over cosine of alpha plus or minus beta. Okay, so go ahead and pause the video and just write out the sum and difference formulas on the top and on the bottom, and I will do the same. So this is sine alpha cosine beta plus or minus cosine alpha sine beta over cosine alpha cosine beta minus or plus sine alpha sine beta. Okay. Now, this is a fine formula, but it's not the one we want. So we want our formula to be in terms of tangents. So I need to get from here to tangents. And now, tangents has denominators, sine over cosine. So I need some cosines in the denominator. So what I'm going to do is I'm going to multiply this by 1 over cosine alpha cosine beta. Again, why am I doing this? Because tangent has cosine in the denominator. And I can't just do that. I need to multiply by a form of 1 to maintain equivalence. Cool, so this is me maintaining equivalence. All right, so now let's multiply this out. It's gonna be a whole big fraction. So this, I'm gonna distribute it out. You could do it on your own, pause the video and then check in, or fast forward, or just do it with me. Sine alpha cosine beta over cosine alpha cosine beta plus or minus cosine alpha sine beta. That's just the same. So that's this term is the numerator, and then this is now in the denominator. Cosine alpha cosine beta. Yeah, and then now I have this in my numerator of this term, cosine alpha cosine beta over the same thing actually, but really this is where I'm getting my denominator from, and then I distribute those two. Sine alpha sine beta over cosine alpha cosine beta. All right, and then now I am almost done. So if I rewrite this, so this term, sine alpha, cosine alpha, that's tangent, and then these cancel. So this is tangent alpha. Just like making a new line here. So this is tangent alpha, plus or minus. The cosine alphas cancel, and this becomes tangent beta. And then this just becomes 1. Minus or plus, and then this, oh, nothing cancels at all, excuse me, and I just get tangent alpha, tangent beta. All right, and that is what I wanted, so I am done, okay? All right, let's move on to sine of a double angle. So we're gonna prove sine of a double angle formulas. These are ones that eventually you should memorize or be able to derive very, very quickly. Either way works. All right, so power, we're not gonna power reduce yet. This is just double angle. This is for the next page actually. So I know sine of 2 theta is sine theta plus theta. So I'm gonna start with what I know, and what I know is the sine of a sum formula. So I'm gonna rewrite this as sine of a sum. All right, and then this becomes sine theta cosine theta. They're both the same. There's alpha is theta, if you will, and beta is also theta. Cosine theta, sine theta. These are like terms, so I just get 2 sine cosine. All right, that's a theta. So that is it, and then we even see in our book that that is an important enough identity that it's written right here, okay? All right, let's do a different type of a power reducing. All right, so we're right here. We want to prove the following power reducing. Especially in calculus, combining exponent, well, we even know right now that exponents make things like a polynomial and sines and cosines make things like a trig. And so you can imagine that having trig combined with exponents adds a pretty big layer of complexity. You know, even if I just said graph x squared, you'd be fine. Graph sine theta, you'd be fine. But graph sine squared, it would definitely take a lot more brain power versus like graph this. This is more simple. So being able to actually rewrite this without a trig function to an exponent is kind of a big deal and pretty powerful. Okay, so if you haven't done yet these problems, you should probably pause and then do these ones, because the first thing we're going to do is use this identity here, right here. All right, so let's write this down and so we can use it. All right, so we're going to use the fact that cosine 2 theta equals 1 minus 2 sine squared theta. So already we see that one side has a trig function squared and the other side has a trig function to just the invisible exponent of 1. So already we can sort of sense the power reducing here. And I'm just gonna solve for sine squared. That's all I'm gonna do. So I'll subtract 1 from both sides. So cosine of 2 theta minus 1 equals negative 2 sine squared theta. I'll divide everything by negative 2. So that looks like, I'll show it like this. Minus 1 all over negative 2 equals sine squared theta. So that, I could leave it like that, but I want it to look like this. So I'm gonna just flip the signs of everything, basically multiply by negative 1 over negative 1, or distribute in that negative to both from the denominator, both my numerator terms. You could think of it either way. So this is gonna become negative, and then this becomes a positive. So I'm gonna write the positive 1 first, and the negative cosine of 2 theta second, and then 2. And I have proven it. Yeah, so that's what we call a power reducing formula, or you could just call it the formula for sine squared theta. All right, so these formulas, this is less of a big deal than the double angle formulas, but still very much a big deal, and you should either memorize them or be able to quickly derive them. They're a big enough deal to be written here. So I suggest memorizing them. If you do enough problems and redo enough problems, you will eventually, mostly, you'll have to do a lot less quote memorization if you use it enough, is what I'm trying to say. Okay, so here, prove this half angle identity. So if I have sine of half an angle, and by the way, one application of this is like, say if I wanted to find sine of 22.5 degrees, say. Well, I know that this is sine of 45 degrees over 2. So if I mean without a calculator, right? So since I know what sine of, you would think, if I know what sine of 45 is there some identity that I can use my knowledge of sine of 45 to find what sine of half of 45 is? And this is that identity. So if you were to actually solve this, just real quick, since we have the identity right here, well, we know it's going to be positive because this is in the first quadrant. So 1 minus cosine of 45 degrees over 2. This would be 1 minus root 2 over 2 over 2. Excuse me. And that's it. If I wanted to rewrite it, I could do 1 over multiply by, I could do 1/2 minus root 2 over 4 if I wanted to. I could do a couple different things. I could do 2 over 4. I could do the square root of 2 minus root 2 over 2, because the square root of 4 is 2. Yeah, so if you were to type this into your calculator in degree mode, and then type this into your calculator, you would get the same result. This is also interesting as a square root within a square root. All right, so that's an application of this, but let's actually derive the formula. So I'm gonna start with sine squared, sine squared alpha equals 1 minus cosine of 2 alpha over 2, which I literally just proved here. I'm just writing it with alphas instead. All right, so, all right, let's start solving for sine of alpha. Sine of alpha, therefore, equals plus or minus the square root of 1 minus cosine of 2 alpha over 2. All right, notice how when you introduce a square root into the equation, that's when you add the plus or minus. So like this does not have a square root. You are the one who introduced it to the equation, therefore you need a plus or minus. If it starts, so if a square root starts in there, you don't like arbitrarily add a plus or minus if it's already there. Okay, so now I'm gonna define alpha as theta over 2 because I don't want sine of alpha. I want sine of a half of my angle. So sine of theta over 2 equals, all right, plus or minus, plus or minus the square root of 1 minus, and this is over 2. All right, and then now I have to say, okay, I want to write this in terms of theta. So I have cosine of 2 alpha, and my question is, what's that in terms of theta? So 2 alpha is equal to theta. So this is like my side work here. Agreed? Agreed. So this is just cosine theta. And I've proven it. So this is my sine of a half angle formula. Let's see if this one's an important one. Let's check my reference sheet. It is indeed. It is indeed. So these are my, so we've learned a lot of new formulas today. And these are all important. And it's gonna make your life a little easier if you memorize them. You could also, like I said, easily derive them. All right, so you're to do that, and then I want to do two more questions. Okay, 2 more questions. So this is not a super important formula. This is more like practicing our techniques to prove novel things. All right, so sine of 3 theta. So I'm going to start with a sum formula. So I'm going to say it's sine of 2 theta plus theta. So go ahead and take a second and just write use the sine of a sum formula. All right, and this is what you should have gotten. Okay, now I'm gonna go ahead and I have formulas for these. So sine of 2 theta is 2 sine cosine, and I still have this cosine theta. So this is that, and cosine theta is there. Now I have sine theta times, and now, all right, so we're right here, and then whenever we have cosine of a double angle, we have to do some thinking. You might not have, I'm not sure if you've proven them yet. It's on this page. So if you haven't done it yet, let me just tell you now that there are 3 different, let's look at this. So there's one formula for sine of 2 theta. So it's kind of nice. When you see sine of a double angle, you're like, boop, this is the formula I do. Tangent of a double angle, boop, this is the formula. Cosine of a double angle, you actually have to think every single time, and you have to think, is this the one I want to use, that one the one I use, that the one I want to use? And you have to really look at your problem. Sometimes you're like, you have to look at where you want to go and just sort of try to see into the future a little bit to what will get you there. So sometimes it's like, I want all cosines, so I use this one, or I want all sines, so I use this one. Or if there's a 1, maybe you use this one, so the 1s cancel out, okay? Now in this case, I'm gonna use this top one. And when let's see, oops, Let's see why. So if I use the top one, so I'll use cosine squared theta minus sine squared theta. When I multiply it out, I'm gonna get this formula. If you choose wrong, that just means when you get to as simplified as you can be and it doesn't match, just go back and choose a different one. All right, so when I multiply it out, it looks like this. Cosine times cosine, cosine squared, sine times cosine squared, sine squared, minus sine cubed. And then these are like terms. So I have 2 sine cosine squared plus sine cosine squared equals 3 sine cosine squared. All right, theta minus sine cubed theta. All right, and we just have one more question left, all right? So we're gonna do this one. And so this looks really complicated, and I could maybe possibly do this by like, well, what is tangent of 4 pi over 3, etc. And what is tangent, but this is tangent of a half angle. So what I want to do is just recall, okay, so recall that I have from the very beginning here, let me look it up on my side here. So recall that I have tangent of alpha plus or minus beta equals tangent alpha plus or minus tangent beta over 1 minus or plus tangent alpha tangent beta. So most of the time when we use these formulas, I'm given tangent of a sum. So like, and then I go to this side, but this is going backwards. So I'm gonna go basically from this side to this side. So I know, so first of all, so let's see, alpha here is 4 pi over 3. Beta here is pi over 12. And then the plus or minus, this is opposite sign, so this is a minus. So this is kind of like tangent of alpha minus beta because of the signs. Because this is a minus, this will be a minus, all right? So this becomes tangent of 4 pi over 3 minus pi over 12. All right, now let's see where this goes, okay? So let's get common denominators. Tangent of 16 pi over 12 minus pi over 12. Tangent. If you want to pause the video and finish this on your own, you can, and then check in with me. That's what I would advise. So this is a 5 pi over 4 angle. In other words, my reference angle is pi over 4 right in there. And so this is negative, positive 1. All right, and that's the answer. And that is the end of my video. Thanks, bye.